So yeah, hi everyone. My name is Kasper, and I am a PhD student from Denmark. I unfortunately couldn't be present at the workshop during this period of time, as I am currently in Italy. So yeah, if something happens with the audio or something, then please interrupt me and let me know. I think I have found a stable connection, but if something comes up, then please let me know. Yeah, so this is my presentation for my PhD work, so related to particle aggregation and breakage within the multiphase Euler-foam framework. So yeah, this is a CFD-PBE approach, so the population balance modeling approach that I will be spending some time on. Yeah, so just some brief introduction. Yeah, as I said, my name is Kasper, and I'm an industrial PhD student from Aalborg in Denmark, and I am employed at a company called Alfa Laval and enrolled at Aalborg University. My supervisors are Kim Sørensen and Jakob Hervig, who are not participating in this conference. The scope of my PhD work is on aggregation and breakage of micron-sized particles in turbulent flows, with the aim of using it for highly accelerated sedimentation on board marine vessels. So yeah, this is meant for marine applications. And just to give a brief background for this work. So on board marine ships, some global regulations became effective by 2020, meaning that the ships could not emit as much sulfur as they have previously been able to. This means that they must either switch to a compliant fuel with a sulfur content of 0.5%, or they can install exhaust gas cleaning equipment, such as a wet scrubber. And this is such a schematic of a wet scrubber, where the exhaust gas enters in a jet section to be cooled, and then it enters this absorber column with a packed bed to have exchange of gas to the water phase. So the water effectively removes all of the sulfur in the exhaust gas, and the exhaust gas leaves as clean gas, and then the water absorbs the sulfur, so the sulfuric oxides. And in this process, it also captures approximately 40% of the particulate mass. And this is then the scope of my PhD. Then what are we going to do with this water that is then this dirty water, and how can we remove the particulate mass from the water phase before the water is discharged into the oceans? Yeah, so some motivation, as space is really sparse on board a ship. We use these high-speed separators or centrifuges to separate the solid phase from the liquid phase. And this application works by spinning around with approximately 7,000 RPMs, exerting the particles to up to 10,000 Gs. And here the most important parameter is the particle size. So bigger particles have a higher settling velocity, meaning they can be more effectively sedimented or separated from the liquid phase. Yeah, so this is the main application we use for separating the solid phase. And in order to achieve an effective sedimentation process, we use this flocculation device, which is the flocculator, where the water, the dirty water coming from the scrubber, is then agglomerated using this static flocculator, which is essentially a bunch of tubes in series, where the micron-sized particles, they can collide and aggregate to form bigger clusters, which are then more effectively separated in the high-speed separator before being discharged into the oceans. So for this workshop, I have decided to present a bit more simple geometrical configuration, where we have a single 90-degree bend. And then the bend has a bend radius of 1 diameter, and we have a an inlet length of 10 diameters and an outlet length of 10 diameters following the bend. And this is just to study the design of such a compact hydraulic flocculate, as it's called in literature, with the aim of achieving a larger particle size distribution. And all of the computational cells in this domain are hexahedral cells with a high quality. So just some brief, some words on the population or CFD-PBE population balance equation modeling approach that I've chosen. I guess most of you are fairly similar with the Euler-Lagrangian approach, where you have discrete particles in your continuous phase. And I also started out using this approach, using a CFD-DM methodology, but I quickly found out that this was not feasible for these industrial scaled applications where the particles were in the range of 1 to 10 microns, because I would very quickly end up with more than 1 billion Lagrangian particles, even for a quite small domain. So I needed to figure out what to do. And I could either choose some coarse graining, but I did not find an appropriate method for conserving the adhesive properties of the particles. So instead, I chose to go with this Euler-Euler approach with the population balance modeling, tracking the number density function. So I just tried to sketch down the overall methodology here. So you can see if you take a cell which is empty, without any Lagrangian points, you would ideally have no particle size distribution function within that cell. So basically, you transfer from having discrete elements, discrete points, to having a set of size distributions in your domain. So that's why you limit the number of equations that you solve to the computational domain, which makes this more feasible for industrial applications. And just to sketch the governing equations here, so it's fairly similar mass and momentum equations, or usual mass and momentum equations for either two-phase or multi-phase Euler. And the noteworthy thing here is this M, which is the momentum exchange at the interfaces, and then of course there's also the source term, which handles different things. But the momentum exchange here I have included is the drag models of WinU, and then the lift force model, a turbulent dispersion model to account for the randomness in the turbulent flow, and also the virtual mass force model. And yeah, I have contributed this Safran Maylift within the multiphase Euler form to OpenFOAM 10. So that is readily available to anyone who wants to take a look. And yeah, so the population balance equation is basically a set of convective transports which tracks the number density function within the domain. So this population balance equation that I have used is a class method, which is popularly called, which was implemented into the multiphase Euler form back in last year by Dr. Ronald Lenig. It is essentially a discretized version of the population balance equation, which means that it is really intuitive to work with, as you are usually used to working with these discretized functions. So having a discretized particle size function, then particle size distribution is quite intuitive to work with. This also means that you can directly see the shape of the particle size distribution within the computational domain. And all of the discontinuous changes, which is due to aggregation and breakage, are accounted for in the source term here. So the aggregation kernel I have found in literature is also implemented into OpenFOAM 10, and is driven by the turbulent the energy dissipation rate, and then the sizes of the particles. And the breakage kernel is driven by the same parameters. So again, the energy dissipation rate, but since breakage is some function of the particle size, shape, etc., then I've chosen to implement this exponential function that has a certain critical energy dissipation rate that is required to cause a breakup within the flow. So at some turbulent condition where the energy dissipation rate becomes sufficiently large, then then breakage will take over in frequency and cause the particles to break up as opposed to aggregate further. And this is driven by a particle strength parameter B, and then the size of the collision radius of the particles. This also means that larger particles are more prone to breakage than smaller particles, which makes logically good sense. So back to the case setup. I have chosen here to present a simulation where the particle range is from 1 micron to 250 microns, and it is discretized into 30 size classes with a logarithmic spacing. And I have been working with a density ratio of 1.4, which seems sufficient since the main particle in my system is soot, which mainly consists of graphite. And I'm working with a fairly low volume fraction of 0.1% and Reynolds numbers of 20,000. So if we look at the results here, you can see how the particles, they will aggregate along the straight pipe section where the turbulent, where the energy dissipation rate is sufficiently low, and aggregation will be the primary driving factor. And as the particles enter the bend, the slope will increase, and at some point these particles will break, and then they will continue to grow after the bend again. So this is what it looks like for this case here. And if we look at the particle size distribution, you can see that the initial particle size distribution then shifts towards the right, meaning that the particles grow in size. You can directly see this particle size distribution within the computational domain. You don't have to do anything about it. So it's really neat. Yeah, and then I just wanted to show some development work. I hope that you can see this on the screen, that the frame rate is not too low. Otherwise, you can also find this presentation on my GitHub, where you can see the videos. But yeah, this presentation that I've been presenting here is a fairly early case that I submitted to this workshop. And since then, I've been working more with different kinds of configurations. So here we have a straight section followed by a bend, followed by a straight section and a bend again. So we have this periodic, infinitely continued geometrical configuration. And you can see how the mean diameter changes throughout the domain, and that we have these linear trends along straight pipe sections. Then we have some breakage due to the curvature of the bend. And then depending on the length between the two bends, then we have different, say, drops in mean diameters. And then you can see up here how the size looks like at the cross-sectional view. And you can see how the mass gradient changes throughout the domain, where you have a positive mass gradient at some regions and a negative mass gradient at other regions, depending on what particle or where the particle is at, and what forces are driving the aggregation or breakage at that point. Yeah, I have some different geometries implemented in this video. Just skip forward. You also have this smaller one here, where we have a different pattern repeating itself. And yeah, remember this is still in development, so it is quite fresh results. Yeah, so some closing remarks from me. This CFD-PBE framework allows to directly analyze the particle size distribution within the computational domain. And you can visibly see how the particles, they aggregate in a linear trend in a straight turbulent pipe, and they break up when they are subject to a sharp curvature where more turbulence is induced. And then I have this ongoing work to determine the best suited designs for these marine installations. And the primary concern here is of course the space needed to make the most efficient piece of equipment that takes up the less space, because space is really sparse on board a ship. Yeah, so all of the source files presented for this 90-degree pipe bend is also published and available in OpenFOAM 10. And you can find it under the Multiphase OilerFoam tutorial if you want to have a look. It's called pipe bend. And the same with the Safman Native Force, the aggregation kernel and the breakage kernel, which are all available in OpenFOAM 10. Just some acknowledgement, big thank you to Dr. Ronald Lenig and Dr. Fabian Schlegel from Helmholtz Zentrum Dresden-Rosendorf and my colleague Anders Simonsen, since they have contributed and helped me quite a lot in the development of this work so far, and yeah, a big thank you to them. So thank you for your attention, and if you have any questions, feel free to ask, or you can reach out. My email is listed here, and as mentioned, my presentation is also available on my GitHub account.
Shall we thank the speaker and then welcome some questions? Are there any questions from the crowd? Well, there's one online. Can you see that?
Just a second, I need to switch here. Non-periodic changes in the bubble sort of mean when it goes around the pipe. Yeah, so since this is a transient simulation, I have to time average over some time or distance in order to achieve a periodic signal, you can say. So the sort of mean diameter. If I just take one time from another, then it is not per se periodic, because you have some distribution breakage function that doesn't give the exact same result every time, since it has to be specified how the particles break up.
Thank you. Are there any other questions from the crowd? Yes.
Yes, exactly. I wait for the steady state.
Thanks for the talk. I was just wondering, how do you get the terms in your aggregation and breakage kernels? You know, the B, I think it was particle strength parameter.
Yeah.
So
this one?
A physical thing.
Yeah, this one has to be, say, specified by the user. So you have to have some knowledge about what your system can do, or what your particles, what the proposition of the strength proposition of properties of your particles are at some point. So you either need to calibrate in like a lab scale facility, or you need some knowledge about the strength of the particles. And in my work, I have calibrated from experimental measurements, but yeah, this is some of the shortfalling still that we need to have a proper way of determining this value based on force models. I would prefer that, but I haven't been able to find a good way yet.
Yeah, they're nodding. Thank you.
Okay.
Any further questions in the crowd? I might ask one myself then. Just I haven't looked at bubbly flows myself, so I was wondering, is there a way, say, in your 90-degree pipe to get a field that looks like the mean free path to precisely see where exactly the coalescence is happening?
Yeah, you could do something. So we have this band here, and you could do something similar to what I'm doing here in the video, where you can see the. So here I calculate the mass gradient from, say, you can say here is one length, and then you obviously have a layer following this layer. So you calculate the difference between two layers. And you could do the same thing for the 90-degree bend, and then you could know where the where the aggregation is driving and where the breakage is driving, because then you would either have a positive gradient or a negative gradient for the for a certain particle size.
Perfect. Thank you very much. No further questions? Well, then shall we thank the speaker one more time?
I have a quick question, if
Yep.
I may ask. Do you observe steady state for all cases, or are there some special cases where you don't observe steady state?
So that really depends on your configuration. I've been working with these kinds of periodic domains, and in these cases, I in the end observe a periodic tendency or a steady state solution, and the same goes for this one. But if you were to have so like for my systems here, I have to time average. But if you're interested in having like the time accurate solution to a certain time, then the signal will not, or the particle size distribution would not be steady state. You have to time average it.
Okay. Yeah. Thanks for your answer.
Sure, you could find applications that are not in steady state. I have only been working with these that goes towards steady state.
Perfect. Okay, so I think that's it now. Sorry.
Okay.
So we'll properly thank the speaker now and let them finish. Okay, so now I have the strange scenario of welcoming myself. So I'm Stefan, and today I'm going to be talking to you about skipping stones in OpenFOAM. So I couldn't help but record a quick demo down on the cam, just so we're all clear about what we're talking about. And so this is work I undertook over about 5 months during my master's under the supervisions of Professor Dalziel and Jasak here in Cambridge. And I have to thank my funders for paying for my master's and lunch. So so a brief outline. So we'll start with an introduction to the problem and the case, then move on to some preliminary studies we conducted and finish with our results and conclusions. So this problem's interesting to us, not only because there's some gaps in our physical understanding of what plays key roles, but also because it provides a good test case for OpenFOAM in an extreme sense, because we have 3 phases interacting, we have extreme gyrodynamic effects, and we also have high Reynolds numbers. So this is a schematic of the stone. So it will have some velocity, which will make an angle with the free surface. It will have some pitch theta. It will also have an angular momentum about the z-axis in the body fixed frame. And during its collision, it will have some immersed area, which will vary as a function of the immersed depth. Then just having a quick look at some of the key dimensionless groups, so the Reynolds, Froude, and Weber number. And for a characteristic velocity of about 5 meters per second and a characteristic semi-major axis A of 5 centimeters, we can see that the inertial forces dominate, and this kind of justifies our neglecting of surface tension throughout this discussion. I also need to introduce 2 further dimensionless groups that are kind of specific to this problem. So we have the contact time Rossby number, which compares the angular velocity of the stone and its contact time with the free surface, and the dynamic state of the stone, which varies between 0 and 1 while the stone is in contact with the free surface. And also allows us to then calculate the contact time. So then moving on to our governing equations, we of course have 2 incompressible phases. So we have a continuity and momentum equation, which I've written in terms of the dynamic pressure, which goes like that, or fairly standard. And then we have a volume of fluid method used to combine these 2 phases. So we have the standard transport equation for the volume fraction, and we have the additional compressive term at the interface acting normal to the free surface. And then we're going to linearly combine the kinematic viscosity according to alpha, but what we do differently here is we do not linearly combine the density. because the forces on the body are really important to us. And so any smearing of the density near the body would greatly affect our results. So this means that we have a jump in the density and a jump in the dynamic pressure across the interface. Then to model the rigid body motion, we use an unconstrained 6 degree of freedom model following TESRA. And this is fully two-way coupled. So the forces on the body are derived from the fluid, and the velocity of the body provides initial conditions or boundary conditions, pardon me, on the fluid. And this is all implemented during a segregated solution algorithm. And then the boundary conditions are no slip on the stone in the frame of the stone. And we use Atkins adaptive relaxation in the far field to ensure that we get no wave reflection. So then how we deal with these jumps in the density and dynamic pressure. So since they're discontinuous across the interface, we can't use linear interpolation, so we throw that away. Instead, we use a ghost fluid method, which involves taking the value at the parent cell center and the value at the near side of the interface of our dynamic pressure, and using that to extrapolate to the neighbor, and then using this to interpolate to our face. And this then allows us to adapt our discretization schemes appropriately. And you could probably do a full talk on how they adapt those. So I'll refer you to Vukovic and Jasak for a lot more detail, or Vukovic's PhD as well. There's a great discussion on that. Yeah, so then taking a look at my computational domain, we have a structured hexahedral mesh, which is developed in pointwise with an OH mesh on the body of the stone. The internal mesh is defined by normal extrusion away from the body, forming a sphere that's about 50 centimeters. And during this talk, I'll consider 3 different resolutions, which are 6 million, 2 million, and 500,000 cells. And just to emphasize the point, we have our mesh moving, and so it will translate and rotate with the stone's motion. And the fluxes induced by this are dealt with using Reynolds transfer theorem and space conservation laws. Yeah, so now we move on to our preliminary studies. So I guess the first question that we had to ask was, which way were we going to solve our volume of fluid equation? And so we compared the algebraic volume of fluid approach with the isoid vector geometric approach for 2 cases, and these were run on our 6 million cell mesh. And we could see that, especially in these rotating cases, there was some interaction between the stone's rotation and the fluid in the algebraic volume of fluid case, where you got these unphysical waves appearing out in front of the stone. And this is related somehow to the stone's rotation, as they do not appear if you choose not to rotate the stone. Also, the wake in the isoid vector case was better resolved. And so moving forward, we will continue with this approach, the isoid vector way. Now, you should notice that there is a slight smearing in the sort of towards the far field of the wake due to our relaxation zones to avoid these wave reflections. And so the next question we had to ask was, is our domain big enough to capture the major physics that we want? And so just to briefly mention how these relaxation zones work, we just linearly combine a given transport operator with a relaxation operator. In our case, that's just setting everything to 0 in the far field. And the weight field is defined by that equation on the right, where d is the distance from our sort of actual physical domain to where you are in the relaxation zone. Yeah, and so, of course, not too much interesting in these figures. You can see that the weights change. However, if you look at the forces and momenta, these are normalized by their maxima. We can see that there are interactions at late times that get increasingly drastic as we increase the size of our relaxation zone, so decreasing the size of our physical domain. And so this basically led us to, again, sort of a natural conclusion, which was that we needed to use big a domain as we could, while also not rendering our relaxation zones useless. So this is why we landed on the 0.15 size for our relaxation zone. And then to sort of validate our research somewhat. So the big issue with this is there's not much work on the subject. So there were no experiments with or simulations done before with a spheroidal stone. So our best option is to do a mesh refinement study. And so we followed Eka and Hoekstra, where you have a discriminating ratio defined by that equation, where S is some integral quantity and the subscripts refer to the fine, medium, and coarse meshes. And yeah, as long as sigma stays between 0 and 1, we're happy. And we can calculate the error following that equation, where or is our refinement ratio for our meshes. Yeah, and so we chose to look at the force impulse, the impulse due to angular torque, I suppose, and the contact time. And so we could see that the error in the force case was tiny, it was fantastic. And then in the impulse due to the torque and the contact time, the error was slightly larger. And also when you looked at these key properties, so if you looked at the change in angles of the stone during the impact, there was some larger discrepancies with reducing mesh size. And this is essentially because the force acts very strongly at the contact line between the stone and the water. And as you reduce the mesh resolution on the underside of the stone, the portion where the highest pressure is at the contact line between the surface and the stone, and hence the force is highest there. And so as you smear that pressure with reduced mesh resolution, the position at which those forces act gets increasingly incorrect, and that's what causes the slightly larger errors in the torque and the contact time with the free surface. Yeah, so then moving on to our results, we'll start with three. Ooh, okay, it's working. Oh, they're automatically playing. I didn't think that would happen. Brilliant. We start with three major regimes, pardon me. The first of which is skip with spin. So this is in the trout regime, is the term that they use. And this is because there is some gyroscopic stiffness, but the stone will still change its pitch slightly during the collision. And importantly for us, the separation point in that upper panel we can see is right where we want it to be, at the point of highest curvature. And in the lower case, we also get some nice asymmetries in the velocity field, which is also expected due to the rotation of the stone breaking the symmetry of the problem. And also either side of the stone, sort of in the middle here-ish, you get these two low velocity regions forming due to destructive interference between waves. Yeah, so it was quite nice. And this is just to highlight again where our relaxation zones are happening and where we sort of stop seeing physical information. Cool, and then we move on to a skip with no spin. So this is interesting because Rossellini, who wrote some early papers on the subject, was performing experiments with cylindrical stones, said that this would never happen. Basically, if you didn't have spin, it would just fall into the water, dive over, due to the lack of gyroscopic stiffness. And then recently, Sai performed more experiments and showed that, at least in a cylindrical stone case, that in fact you can get some skips for some regimes. And we were able to also show, proving sort of, well, disproving Rossellini's assertion even further, that you can in fact get a skip with no spin, which is good. Now, some comments on this is that due to the lack of gyroscopic stiffness, there's a really sharp change in the pitch of the stone, causing quite a severe impact with the free surface, and that causes the separation point to change and also the surface to break up somewhat. And in this case, we need further experimental results to know if this is physical, we would say, fully. Yeah, so cool. Moving on from that, we have our next and final key state, which is a surfing state. So in this case, we have a sort of an intermediate state between failure and success. And in this case, so the stone will have a very long contact time with the free surface and then eventually go below. That was outside of the realms of computational expense for us. So you could see that this has the extremely long contact time and it does oscillate. But due to the fact that we have sort of current number restrictions when we're dealing with the iso vector method and the fact that this will never leave the contact with the free surface, it costs a lot. Nevertheless, we're quite happy with this. We can see that the free surface is breaking up as the stone is spinning consistently, which is very nice. And we also have the contact line again in the correct place, or not contact line, pardon me, separation point again in the correct place in the upper panel. And we also see these larger waves forming, which we think is due to the increased pitch. However, the sort of strange behavior of those waves is because the mesh resolution, as you move further and further away from the stone, gets coarser and coarser anyway. And so we don't quite have the resolution to get the film as it tends towards the far field. Nevertheless, we were quite happy with being able to simulate these three key states. And then we moved on to sort of commenting on the lift models that exist in the literature for these skipping stones. And these lift models were developed sort of experimentally or theoretically and referred to spherical cylindrical stones. And so yeah, initially Bouquet's was a quite straightforward lift model. Rossellini added some dependence on the pitch and angle of attack, and then Tang came up with a slightly more complicated constant where C it was tuned, and alpha there is derived from linear analysis of flow past a wedge by Squire at some point in the 1970s, I think. And lambda is the aspect ratio of the wetted portion of the stone. And so then to apply these to our model, we had to change how their sort of analytic expression for the immersed area worked, which was nice. And this was important to know that the separation point was indeed where we expected for these cases. So we could use that to calculate or to write down this expression for the wetted area, where E there is the elliptic integral of the complete elliptic integral of the second kind, and B is the semi-minor axis that hasn't popped up yet. Yeah, and basically when we compared these models to the lift force we got from our simulations, we could say that they needed further work, and it was the assumptions that they made regarding a relative level of gyroscopic stability, and also sort of complete neglect for any out of plane motion of the stone. So they didn't even consider any roll. And so both of these need to be taken into account to improve this. And then finally, I'm not sure, how am I doing time? Okay. We had some parametric studies, and I'm just showing there was a lot more parametric studies, but these are the nicest results. So when you varied for a small initial roll, you found that there was a linear relationship between contact time, and when you varied the initial velocity, you could find there was an inverse proportional relationship between contact time. And this then implies that there is a inverse proportional and proportional relationship respectively between to the contact time Rossby number, as in both of these cases the angular velocity was fixed. Yeah, and so then to conclude, I gave a brief overview of NavalFOAM's volume of fluid goes fluid method-based solver, discussed the preliminary numerical experiments and demonstrated some successful simulations of key states and showed results of our parametric studies. In terms of future work, we need some experimental analysis. We would like to increase the resolution further to fully resolve boundary layers, improve the theoretical models, and optimize the design of a stone to skip is the sort of major goal. Yeah, so thank you very much, and I'd love to welcome any questions. Yes, Herv.
I wanted to ask you about the experimental work for this, because if I wanted a study which is unrepeatable and an absolute experimental nightmare, this is it.
Yes.
So can you comment on the quality and consistency of the experimental results that you use?
So they're quite, shall we say, qualitative in nature, at least from what we've seen. And so my other supervisor, Professor Dalziel, is quite an expert in experimental fluid dynamics here in the maths department. And so he's currently working on designing his own experiments in collaboration with Stephen Turnock down in Southampton, because Professor Turnock's got a nice, very large tank that we would hopefully be able to do this in, but it would take a lot of work and be very, very, very challenging to create sort of consistent, reproducible data sets. Yeah.
Thank you. Maybe a stupid question, but since I never managed to let a stone skip, it is possible to use your results or your future results to build like a slingshot for the perfect skipping stone.
Yes, yes, exactly. So you can, especially in our parametric studies where there's some further results, you can essentially optimize for the angle of attack and the initial pitch, which seem to be two of the biggest factors, but there's also the initial roll, which has a great effect. And this, we were the first people to look at this at all. So there's still definitely some work to be done with regards to that roll. But we were finding that actually, if you gave it some slight sort of tilt this way as well, that would improve your results. So yeah, but the phase space is huge. So there's a lot of, you could optimize the hell out of it if you wanted to, and spend years and years and God knows how much computational resources doing it. But yeah, can definitely make it a little bit better.
Hello. Yeah. Okay. This is more of a comment for your question. There is a video online by Mark Rober where he has done a series of, it's much more of an experimental basis, where he has built a robot that does exactly what you're talking about, but I don't believe it's coming from a fluid dynamics point of view. So I'm sure there's a contact point there that you can explore this further with.
Yeah, no, and that robot, so there was a group in France, the Bouquet and Rossellini, so they also had sort of a similar robot, first spinning up the stone and then releasing it. But there wasn't necessarily optimization done there. That was just sort of some very initial experiments with some sort of rough selection of the parameter space. And the major critique I had of their work was they used exceedingly high angular velocities so that the stone was gyroscopically stiff. but like a human would never be able to reach those like rates of angular velocity. So
Are there any more questions?
I have a question. Yeah, so it was really nice results, but I still have no clue what are the hydrodynamic forces at play here. What are the interactions between the solid and the liquid? Any comments?
From a fluid dynamical, or like how I'm resolving them, or from a fluid dynamical perspective?
Yeah, fluid dynamical perspective, yes.
So it's mainly the pressure force. There would be some viscous forces, but those would be significantly smaller. So it's mainly the pressure forces cause the motion of the stone. That and coupled with some like minor Magnus effects as well. Yeah.
Okay.
Does that answer your question? Sorry.
Yeah, it does, but it's not really that. It doesn't completely give you the picture because there's something else going on, right? There's a competition between, I guess, contact time and how much it can stay over water. Is it that?
Yeah, I suppose, like, yes, Herv.
I would like to comment. We have a full CFD solution. So that means that you have the pressure field and the velocity field, including the viscous stress for every time step of this simulation. So in fact, the forces are fully known. And I think what you refer to is the integral of the impulse of the pressure force, which depends on the global parameters. So locally, we know exactly what's going on, but that's not the same as knowing what to optimize in order to get, to preserve the pitch angle or to get the highest height after the bounce. Okay, but the solver is there. It's written from first principles. It's an ODE equation. I think we can ignore the fact that the stone will deform in impact. We can ignore any compressibility effects. Surface tension effects have been taken out. It's just a question of running the code enough times until we understand what we need to do. I'm sorry if the answer is terrible, but that's how I see it.
Yeah. That's a good enough answer from me now. Thank you.
Maybe a short question on the non-rotating disk. Why is what breaks the symmetry in this case? Because the flow field was.
Yeah, no, that's a good question. So our current idea for why that was the case in that simulation was simply because as that surface is breaking up, we can't resolve all of the droplets. So we would assume there would be symmetry, but if we're not resolving all of the droplets, there would be some sort of, discrepancy between that and reality. But yes, yeah, good question. Yeah, I think we need to move on to the next speaker. Perfect.
So good afternoon. I think I have another talk tomorrow, so you didn't quite get rid of me, but I will try not to be too boring. I'm talking on behalf of my student, Robert Kesser, at the University of Zagreb. And we had quite an exciting project on Eulerian multi-fluid sprays. The project was set up in collaboration with King Abdullah University of Science and Technology, called KAUST, based in Saudi Arabia. And if you're an experimentalist, this is heaven. So they have the best, the most expensive, the most detailed experimental equipment that you can possibly imagine. And Professor Battistoni from University of Perugia is looking at modeling things at the LES level. And the thing that we are looking at is multi-component dense sprays. For those of you who have done combustion and internal combustion engines, you will know that gasoline or diesel fuel comes as a mixture of a huge amount of components,
and that it actually varies from well to well. And you have to inject that into the combustion chamber. It needs to evaporate, and then it needs to burn. So when we do experimental comparison with that, instead of gasoline, we will use octane, and instead of diesel, we will use heptane, which is a single species fuel, and then everything behaves much nicer. However, the 21st century is upon us, and rather than using simple fuels, we want or need to use complicated fuels. So the first one will be something like addition of ethanol that you can grow out of corn or similar into the fuel that you're using, or indeed doing some more bizarre tricks like adding hydrogen microbubbles into your fuel and seeing how that affects the performance. So now suddenly, rather than having a uniform single species fuel, we have a mixture of different components with significantly different evaporation rates. And what that means is what you're burning at the start of evaporation is not the same as what you're burning towards the end of it. The second part of this is my pet hate of modeling diesel sprays. And in the 1990s, when I got involved in this game, we would use Lagrangian particles. So you would say a Lagrangian particle is traveling through the mesh, integrating mass, momentum, and energy exchange, very similar to what Stefan was showing. But rather than having a geometry, it would be represented by a point. And the problem with that approach is that you can assign 1 liter of liquid to your droplets and put it into a 1 cubic millimeter cell, and the model would not break down. Okay, this is clearly wrong, and it is particularly wrong in the regions of a dense spray. So the modeling approaches that we are working with need to concentrate on being able to deal with the entire spray in an old-fashioned machine like an internal combustion engine. So to give you an idea of what's going on, in a modern diesel engine, you're going to have a common rail injector. It's the part on the top of the screen. And you will be injecting the liquid at the pressure of about 3,000 bar. And for me, just conceptually, what's coming out of that nozzle is not as clearly known as I would like it to be. 30, 40 years ago, if you're injecting at 300 bar, I don't really have a problem with that. But with 3,000 bar, this fluid is likely to cavitate, flash boil, strip out into very small shapes, which will then further break down due to inertial forces. And you need to find out what's going on. So the length of that liquid core will be in millimeters, okay? And if you imagine describing this dense region here really doesn't work with Lagrangian particles. So to give you an idea of what the spray is really doing and what the Lagrangian particles are modeling, in a single injection of a diesel spray into an internal combustion engine, you will be injecting below 1 milligram of fuel, and you will have more than 2 billion droplets. Now, clearly, I can't have 2 billion Lagrangian particles. So what I do is I say, well, let's have 300,000, and each Lagrangian particle will represent a distribution of droplet sizes, which are then subject to injection, primary breakup, secondary breakup, momentum exchange due to drag forces, breakup and coalescence, eventually evaporation in order to create a mixture, and then you're going to burn it somewhere here and indeed on the sides. So the naive way of modeling this is to say, well, let's just start with my Euler-Lagrange model, where I have some big droplets, small droplets, etc., which then undergo a series of processes. So to account, for example, for momentum exchange, I will introduce a drag force on each Lagrangian particle. I will follow it into the cell and out of the cell and find out whether it accelerates and decelerates, which gives me the force acting on the particle. And then the other part of that force I will impose onto the continuum in order for the droplets to accelerate or decelerate the flow. The second thing that I will do is I will look at droplet-droplet interaction. But in order to help myself with a large number of droplets, I would say that the two droplets that are in the same cell interact with each other, but that one doesn't see a small droplet in another cell because it's just inconvenient for me to search for them. Okay. And the third thing is because I don't have enough Lagrangian particles, I need to account for the fact that each of these droplets are representing a population. So not great. How about a different modeling approach? And that would be direct numerical simulation. So you've seen a lot of free surface flow, including Stefan's. And the requirements that we need to have is that we resolve the free surface. Okay, if we do that, solving mass, momentum, and energy will be a good job. But that means that I need to have, I don't know, 5 or 10 cells across the diameter of a single droplet. And my droplet is very much sub-micron. So in fact, I cannot do this. With the Lagrangian approach, I already told you that the droplet will be a point in XYZ space, moving through the mesh, carrying a mass, and it doesn't have this interaction with the background phase. So what we decided to look at is the idea of an Eulerian multi-fluid model. So the one that you have seen from Stefan is already an Eulerian multi-fluid model, but it is special because there is an interface between the water and the air, which is resolved on the computational mesh. So rather than doing this, I will say that my Eulerian multi-fluid model contains a series of interpenetrating continua. Okay, I think I have a slide on that. And the idea is that I'm going to have the background phase, which is present everywhere. And then I'm going to have a dispersed phase for my droplets, where I'm going to say what the droplet diameter is. And similar to the volume of fluid approach, I'm going to have a volume fraction approach, saying that, I don't know, 1% of this cell is filled by droplets of a given diameter. And based on the diameter, I can calculate the drag force, which is my momentum exchange, and track the population through the system. That sounds pretty good. But in order to do what I need to do, I need to specify the diameter of the droplets that are in the system. And that would be called a mono-dispersed Euler-Euler system. Well, that's no good, because I'm going to have small droplets, medium droplets, large droplets, super large droplets, and I still need to account for all the effects that I told you, which is basically mass, momentum, and energy transport. So in a polydispersed way, we are going to introduce a series of species of different droplet size classes and make them talk to each other. Conceptually, you can look at this mass fraction of a single size of droplets in your domain in two ways. It's either the real mass of droplets, or it is the probability of the presence of droplets of a given size, which gives me a really nice way to communicate within the system. Further, because I am dealing not with points and diameters, but with volume and mass fractions, I can make sure that the continuous phase realizes when there is no place for it in the dense part of the spray, because it will basically be ejected by the droplets. So what we have are interpenetrating continua, and both phases are specified in the Eulerian reference frame. Because the droplets can significantly vary in size, I have to worry about the size distribution. And here I put I pulled rank on my students, and there are two possible approaches to it. The first one is called the method of classes. And it basically says, I know that my distribution will go from 0.1 micron to 1 millimeter droplet, and I'm going to group them into classes. So from 0.1 to 0.2 microns, 0.2 to 0.3, etc., all the way to the maximum radius. And for me, this sounds very appealing because you don't have to worry about what is happening with the distribution. And provided you have enough classes, you can capture any distribution in the system. Well, what's enough classes? Is 8 classes enough? Well, not really, because if I'm starting from really big droplets to really small droplets, I may end up with not having enough resolution in a droplet size space to find out what the physics is doing. So an alternative approach to this is something called a population balance or moments of curvature approach, where you're going to have a continuous distribution of sizes that you will parameterize in terms of pivots and weights, which can shift the distribution in, I don't know, a beta PDF spectrum, which allows you to go from one extreme to the other. I have to say that this approach is better, but for me, it is counterintuitive. When I have a set of classes, I can tell you that the breakup model says that the big droplets conservation or mass conservation equation is going to have a sink term. And when the big droplets breaks down, it is going to appear as a source term in a smaller size. With population balance described with moments, quadrature moments, or discrete quadrature moments, this is much harder, and it made my head hurts. So we decided to go with the method of classes and afford as many of those classes as we can. So for each of the droplet sizes, I'm going to have an individual momentum and continuity equation. What's the reason for that? Well, the reason is that each of the droplets exchanges momentum with the background phase. So if I just let them drop down like the rain, their terminal velocity will depend on their radius, which means just that each of the droplet sizes needs to have its own momentum equation to couple it. So for the pressure, we will use the mixture pressure equation, which allows us to get away from worrying about mass conservation and various other coupling effects, but it also kills issues like being able to deal with surface tension. So let's just step into surface tension a little bit. If I'm looking at this polydispersed model, I will approach the droplet from one side and I'll have the gas pressure. When I get across the interface, my pressure will jump because of the surface tension, which depends on the curvature of the droplet. And when I get out on the other side, I'm going to end up in the continuum pressure again. So in fact, by knowing the diameter and knowing the curvature, I will be able to account for the fact that the real pressure inside of the droplet is larger. But when you think about it, that pressure is not going to make the droplet move because the integral of the surface tension force is 0. So let us take a look at some of the closure models. Oopsie. Okay, so I will start with a very dense spray where I can have something called the liquid core here, which is basically a continuous part of the system. Then I'm going to create droplets of a certain size, which will then break down further and further until I get into the very dilute mode. So the moments, the sub-models that I need will deal with interfacial momentum transfer, mass transfer, energy transfer, and modulation of turbulence. So the mass transfer will be breakup and of course coalescence if you need it. The mass transfer terms are basically sources and sinks between mass fraction or volume fraction equations for each volumetric size. There's also evaporation. when I heat up the system, eventually I want to produce gaseous fuel. So I need to take into account evaporation model. On the interface, I'm going to have drag and turbulent dispersion term, which depend on the range of scales between turbulent vortices and the droplet size. So here's my phase-intensive momentum equation. And the left-hand side, you will recognize Reynolds stress, pressure, gradient, gravity. And then I have the two last terms, the first of which is the interfacial momentum transport. And to deal with that one, I need to deal with droplet drag. And in order to do that, I need to know two things. First, I need to know the droplet diameter, which I can calculate backwards from the mass fraction. That gives me how many droplets I have. And the other one, I need to have a form of the droplet. Well, I'm scared. And when I'm scared, I run away into spherical droplets, calculate the drag law using something like 64 over Reynolds or something similar, and basically close the system. There is also virtual mass, lift, force, etc., but we are not taking those into account at the moment. With regards to the momentum source term, due to mass transfer, you need to take into account the fact that when the droplets break down, the energy from the broken droplets will end up as a source term in the momentum equation on the other scale. Or indeed, if you evaporate a part of the mass, that will take a part of the momentum away from the droplets as well. So here, we can deal with the momentum source terms. Is this better or worse than the Lagrangian models that I started with? Well, in fact, it's the same, because the models that we need to run still do the same kind of thing, but now rather than acting on particles which move through the mesh, they appear as volumetric source term. So the reason why we do all this is to be able to deal with breakup, coalescence, and consistency in transport. So one of the things that Robert did that I really liked is to take the volume of fluid equation that you recognize from Stefan's presentation in a multi-phase form, and you have the terms on the right-hand side which couple them across the system. Well, this is beautiful because we can account for compressibility and for source terms of breakup and coalescence by solving these equations in a block coupled manner. So I can take my 50 or 100 species, put them together into the system, and rather than solving them one at a time, I solve the whole lot together because that couples the source terms and the diagonal terms, making sure that I don't have any inconsistency in the transport. The second one is the phase intensive energy equation. Well, why can't I have one? Because the heat transfer rate depends on the local velocity and it depends on the droplet radius. So now suddenly I have to carry a different source term for each of the droplet size classes. So suddenly what I have is one background phase with continuity equation that gives me shared pressure, momentum equation, mass conservation equation, and energy equation. And then I have a set of momentum, energy, mass conservation for each of the dispersed phases. Okay, so that's quite a price to pay, but it allows me to deal with the system that has polydispersed nature. So further to that, I can have the phase intensive species transfer. And this was really the kicker of the project, because if you have droplets of a different size with differential evaporation of certain species within the system, I need to deal with that. So how do you deal with that within a Lagrangian system? Well, it's tough because you need to solve a coupled diffusion 1D system across the radius of the droplet to find out what's going on. And here I can do the same by solving species concentration within each phase I and component J, And in order to do the closure, I basically need to deal with the species source term. So basically, we managed to couple all of this together. I think I'm going to skip the part about turbulence modeling because it just complicates the system even further. And take a look at the thermal modeling. Okay, so within the thermal model, we need to take into account the heat exchange between the background phase and individual droplets. And that includes the temperature profile across the droplet radius. Now, within this temperature profile, you're also going to have a bunch of species, and the diffusivity of each individual species can also depend on the temperature. In reality, you're going to have intensive recirculation within each droplet, but this is beyond the stuff that we can solve. So we will model that by introducing effective thermal conductivity correlations that you have here. So the last part of the system is the high Weber number breakup model. And that will basically take into account the interaction between aerodynamics forces and surface tension forces, which will tell you how surface perturbations develop in time and how the breakup happens between droplets of a different size. They will appear as the source term, showing you how the radius of individual droplets changes in time, with breakup time, wavelength, and growth rate given here. Sorry, running out of fuel. So in terms of evaporation modeling, we again have the issue of fuel vapor near the surface of the droplet being saturated, and that allows us to put together the evaporation model. Okay, so in terms of multi-species evaporation, you still have to take into account the species transfer for all individual phases, both in droplet and the gas. And that was the whole point of the model, because we need to look at differential evaporation. And that has been implemented using the discrete multi-component or DMC approach, which basically satisfies our needs, but it is a probabilistic model rather than deterministic. Okay. When you look at all of these things happening together, there is a whole set of secondary things happening within the system. For example, if I have a parent droplet with a certain decomposition and it breaks up into a child, how are you going to split the decomposition? Well, I don't know. So in the first approximation, you say that the child composition is the same as the parent composition, although this is not necessarily true, because you may be stripping the child droplet off the surface, which may hold more concentration of certain species. So the model has been implemented from scratch. It is tested in the stages that I mentioned. So we start with the monodispersed model, include multiple alpha equation for polydispersed. We start doing non-evaporating sprays and eventually start evaporating the sprays. So here are just some pictures of how the system hangs together. For evaporating sprays, we have a compressible formulation, and the results look something like this. I think I'm running out of time and running out of steam as well. So let's just stop it here and give you a chance of asking some questions. Where we stopped with the work is we never actually lit this. So the combustion part is still left for future work. Thank you for your attention.
Yeah, so if we do maybe one or two quick questions and then keep rolling because we're running a little bit behind.
Hi, just a couple of questions on a diesel spray in particular. First of all, it's shown as a continuous spray, but in a diesel engine, you might have, say, 8 different injection events, like a pilot's injection, a couple of mains and post.
I'm sorry, I didn't quite get it. Can you just put the mic straight in front?
Okay, so
you were talking about the diesel spray in an engine, right?
Yes. So instead of doing a continuous spray, they will have like multiple discrete injection events.
Mhm.
Is there a particular injection event that you're modeling in this case?
This was targeted towards the experiments done at KAUST, which was a single shot. Okay, but if you have an injection profile or multiple holes or any combination of mass flow rates, this is just a temporarily varying boundary condition, which is not a problem.
Okay. And the next thing was you mentioned at the end about the combustion. I understand you haven't implemented it, but is it feasible to have like a global combustion model?
Yes,
or does
indeed.
the chemistry need to be implemented for each different class of droplet size?
Okay, so the result of that model that I showed you so far will be mass concentration of individual species of a mixture in the continuous phase. And you will always burn it in the continuous phase. So you just have an inhomogeneous mixture where you need to run a combustion model. And I would assume that that would be a combustion model from first principles, which is probably truly expensive, but this is a diffusion dominated flame anyway. So I'm afraid there is no shortcuts here. Okay, well, thank you. Please allow me to run away now.
Next, we'd like to welcome Thibault Oudart. Apologies if I'm mispronouncing.
Hello, I'm Thibault Oudart. I'm a CFD engineer from Artelia. I'm sorry I changed a little the title of this presentation because when I sent it, it was I just began my new job. So since January, I've been detached from Artelia at half time in the LEGI, the Laboratoire des écoulements géophysiques et industriels, the Laboratory of Geophysical and Industrial Flow. And I am paid by France Relance. It's a project which allows company to make some research in industrial laboratory. Sorry. So why we want to study that is because in Artelia we make a lot of simulation of inundation with Telemac. Also some CFD, and Air-Entrainment frequently found in nature and also in industrial flow, and we need to understand it well and be able to reproduce CFD, to use CFD to have this kind of mixture. So what happens, we have a high potential flow with transformation from potential to kinetic energy, and this generates turbulence and disturbance of the free surface, and the air will be entrained into the water. And the consequences are we can have risk of destruction of structure, of flooding, and sometimes underestimation of water level in river, or also some damage in pipes when there are inside. The problem is we have large spectrum of interface from bubble to river, and also we need turbulence. So we want to treat this in 1 year. So we want to have a simple case, so simple problems with low number of input parameters, simple geometry. We want to try to model this with fine turbulence and fine mesh with LES, and then go back to a coarse mesh with runs and going from LES to runs, and add some diffusion in runs model to be able to be comparable with the LUS results, and then go back to industrial flow. So little outline, I will talk first about physics and numerics, and then talk about two cases, jet with in laminar and turbulent, and then a little about hydraulic jump. We just start a little. So what is the aeration? It's when we start. Okay. At the point here in this diagram, it's a Brookini diagram where the vertical axis here is the fluctuation velocity, and the horizontal axis is the dominant characteristical length at the free surface. And when the velocity increases in this type of diagram, we travel from A to B, with its an increase of turbulence inside the domain and the decrease of the surface scale, surface deformation scale. When these deformations are too small, the aeration starts and air go inside the water, and we have bubble, and the turbulence increase a lot. So Jasak already talked about this just before, but we have here two important numbers, the Weber numbers, which is the inertia, the rapport between inertia and tension, and the viscous force, and the capillary number, which is the ratio between viscous force and tension. And here we have the Kager representation of a jet here impacting a bath of a liquid. And in function of the case, we will have different scenarios, different things will happen. If we are in laminar, the net viscous force, we call the surface tension, and we will have this kind of trump which will appear near the jet. When we are in turbulent, the turbulent perturbation of the jet will create bubble inside the bath. So the problem for modelize that type of simulation of multiphase flow, it's the large spectrum of interface. We have bubble inside water, bubble of air inside water, but also the free surface, which can be metals. We need to have also the mixtures, the air inside water. We have also the dynamic of air bubble into water, and this is also complex. And also the Rance model idealized the turbulence, and therefore will not be able to disturb the free surface to have air inside the water. And also, as already speak before, we can have different type of identification of the interface. We can really identify it if we have an undefined mesh, or we can also modelize it like here. We use two types of server, Interfoam and interIsoFoam. So Interfoam use mul scheme to compress the interface. And interIsoFoam is isoed vector scheme. So the interface is first compute at the first time, and then is propagate into the cell at time t plus dt. So the jet, it's a jet. It's just a circular jet with a wet fluid with an initial velocity which fall into a bath of the same liquid at rest. And as shown here, by the sharing of the free surface, an aeration zone will be created around the jet. Bubble will be entering into this bath. So why we choose to try to modelize this? To model this is because it's very simple shape. We need a few parameters: jet velocity, fluid properties, and the initial diameter of the jet. We can find a lot of laboratory results, and we didn't really need initialization time or very small time. We work in two cases. So a laminar case from Lorenzo et al. At the left here. So here we can see some pictures of their experiment. And we work also in a turbulent case with high velocity from Chanson here in 2003. So for the laminar case, the pictures we can see here, it's a case with silicon oil. So it's the dark here, the jet, and it's the bass also, and air here. And for this case, they have a diameter of 1.5 millimeters. Velocity of the jet is 1 meter per second, but the air film thickness, so what happened here and what we can see here, the H here, it's about 5 micrometers. So it's too fine, it's too small for us to go to have these diameters, and to reproduce this thickness, we will need about 2.5 billion of cells. So we cannot try to reproduce this, and we choose to use the second case. So it's glycerol and silicon oil. So the jet is glycerol on the base also, and the surrounding liquid is silicon oil. For this case, the main advantage is the velocity a little slower, 0.1 meters per second, and the film thickness, the H, is very bigger. It's about 1 to 2 millimeters, so same order of size than the diameter. But we haven't got any pictures of this case from the Lorenzo paper. And we use the motionless calculation to avoid to have too small cell. So this is the mesh. We use a wedge mesh, so we only make a small 2D case, near 2D case. We use 10 to 20 cells in the jet diameter and an uniform inlet velocity. For this case, laminar case, we use only interIsoFoam with second order on time and space. So we can see it's only a small part of the jet. So here it's the jet inlet, and the water level is near here, the bass. So this is a result. So we can see in blue the glycerol, and at top the silicon oil here, and here glycerol, it's silicon oil, and so the pictures are from for silicon oil and air, but we cannot reproduce this. So we have the different state, but it's only qualitative. If we look a little more closely, first we have the particular shape where the trump is very large, and then when the flow go inside the bass, here we will the shape is little smaller, little center, and then go down. What we can see is also the velocity here. In blue, the velocity go down, and then in red go up, and it's very comparative, almost qualitatively, as what show Kiger in his paper here. To have something which looks like a little more like what they done in their experiment, we increase the jet velocity, so it's not the same experiment that they have done with glycerol and silicon oil, but it looks like a little more what they saw for silicon and air. So again, we have the velocity following the jet here with go down, and then larger velocity go up with slower velocity. So the second case is a turbulent case from Chanson. So this time the velocity is higher, same order of diameter is a little bigger, 2 centimeters, 2.5 centimeters, and it's water and air. And what we will compare it only the void fraction into the bass. So this is a scheme of their experiment, jet, and they look here the void fraction at different depths. So for the mesh, this time we make a 3D mesh on different level of refinement from 1.2 million cells to 20 million cells. We haven't run actually this model, but we will soon. We also use the two solver Interfoam and interIsoFoam, and 3 models of turbulence. Once LES, we will try also different scheme in LES, and also hybrid EDD-ES, always with second order on space and time, with Frank Nicholson, fully for second order. And we use a fully developed profile in inlet. So we create a 2D case to just allow the profile to be fully developed into the inlet. So here's a little scheme of the case. So we have atmosphere at the top, wear all around, and free outlet here. So this is only void fraction at different depths for different cases. So the blue are the experimental result from Chanson, and we compare the void fraction at so here in the middle is the middle of the jet, and one is corresponding to the rear of the jet. And what we can see is that from LES to EDDS, we haven't got a significant improvement, but to go from the coarse mesh, which is called level 1 to level 2, improve greatly the result. So we are more sensitive to the mesh quality than to the mesh refinement than to the turbulent model for this, for LES or EDDS. But we also saw that we well reproduce at the top of the bass, we have a lot of void which is entering, and this void decrease in peak volume, but go larger. So this is only a slice view of the result for different turbulent model. So the best result we have obtained is for this case at the bottom right. So we have instant result of water and air bubble in white and water in blue. So this is the best result we have obtained for LES Magorinsky, which is the finer mesh we have tested until now. And what we can see is for the runs case, we have the amount of water of air in train is very, very estimated. And one of the problem is when we have too much air in train, we will also have too much air which go up and perturb the surface and then increase the amount of air in train indefinitely. So then we will switch to hydraulic jump. So first, it's the first case we want to do when I start 5-6 months ago. It's to do this case, but it's a little more sophisticated to control exactly where the hydraulic jump will be. So we go first to the jet, but finally it's exactly the same type of case with what we can see here. At the jet position, at the hydraulic jump position, we have a pinch of the air which will go inside the jump. We have done some simulation in 2D just to compare interfoam and interIsoFoam for this case, and to look if we find the same position of the hydraulic jump. So in 2D we have the size of the bubble are overestimated a lot, and we start slowly to do it in 3D. So it's a close mesh with 1.5 million cells and in runs, but we will just start to define where we need to refine our model, and we will then try to extract the void fraction and be able to compare result from 2 experimental results. So the short conclusion, we are able to reproduce Air-Entrainment well with high resolution mesh, but what we want is now to try to go back to coarse mesh and improve them, improve result on them. So we will first do a lot of combination of turbulence, solvers, and mesh to create a matrix of results, and then try to go back to the ones with a model of Air-Entrainment into it to improve our result for this case, because it's what we use in Artelia and in industrial flow of geophysical flow mainly, perhaps no industrial, but geophysical industrial flow. We cannot use LES. It's too cost. It costs too much for us to use this type of model. And to finish, I will just present this little add-on we are building it. We are work on it actually. So it's an OpenFOAM reader inside Blender to be able to visualize and manipulate your result and produce some video directly from our result. So this is the case I presented before, the laminar case. Thank you.
So again, maybe one or two quick questions because we're running behind, and then save the rest for over coffee.
As a short comment, we worked on similar problems with a student, so you may find it interesting to read the PhD thesis of Silje Almeland from Norwegian NTNU, Norwegian University of Science and Technology, I think. So yeah, could be interesting for you to check it out. My question is about the IDDS.
Mm-hmm.
In what sense are so how do you use that for such a problem? Where do you have the RANs and where do you have the LAS?
Here, so we have LES almost anywhere in the area of interest. We just look after simulation, we can see where is the blending between LES and the RANs. So it's near LES pure LES.
Okay.
Because we have already defined our inlet. We create a small inlet, which it's a cyclic, so we have a very fine inlet velocity distribution and turbulence, which is used directly for the inlet of the model, big model.
Okay, thank you.
If there's one more brief question, we could take that. Otherwise, yeah.
Hello. Would you mind telling us the difference in time, roughly, between using Mulsa or isolate vector? Would you mind telling us roughly the amount of time it took to use isolate vector in comparison to Mulsa? So between Interfoam and interIsoFoam?
Yeah, I have some results comparison between the both, but I haven't have the time to put.
Because one of your slides was Mulsa was faster. So faster by how much?
Sorry.
No problem. One of your slides says that Mulsa is faster. Yeah, when compared to isolate vector, by how much? In your case, 2 times faster. Thank you.
So shall we thank the speaker again? And yeah, we thank you, Ricardo. Well, welcome, sorry, Ricardo Ribeiro to the stage.
So should I start?
Yes, please.
Okay, so my name is Ricardo Ribeiro. I started my PhD recently at University of Minho in Portugal. So I would like to thank my advisors, Miguel Nóbrega, Ricardo Costa, and also Bruno, and all other my colleagues. I will present my work, which is called Assessing Injection Molding Simulation in Footwear Industry. Okay, so here's the outline of my presentation. First, I'll do a brief introduction. Then I'll talk about computational methods, including interface tracking, viscosity model, compressibility, and permeable wall boundary condition. Then there are some case studies and results, and I will talk with you about my future work. So this project is a research collaboration between University and Minho and 23 partners from Portuguese footwear industry and academia. It is called Green Shoes 4.0, and it has the main objective of try to achieve industrial digitalization in this industry, because this is one of the top industries at Portugal, and I think it employs over 100,000 individuals. And why we need to achieve this digitalization? Mainly, I've worked in footwear industry for some years, and what I've noticed is that most of the activity is still based on trial and error approaches, which are quite expensive in terms of time and money. And so most of the times we are dependent of the oldest guy in the company, but if he's not there, there will be a problem. Also, the shoe soles injection molding requires a large investment in machinery and molds, and it has a very narrow margin of failure and a short time to market. And this is due to the fact that it's a fashion product. Some of you may know how it works, the injection molding of thermoplastics. Basically, we have polymer pellets, which are in solid state. They are deposited in a hot heated cylinder, and also we have a screw which will push the molten polymer inside the mold cavities. Okay, so in this work, we are starting to introduce computational methods in order to guide us in the optimization of the manufacturing processes. And also we can use it to, for instance, do project of molds and to understand how to get the ideal processing conditions regarding temperatures, flow profiles, pressures, cooling rates, and some others. And we want to minimize the trial, the time and resources spent in experimental trials. So one of the most prominent defects in the shoe soles injection molding is the entrap there, bubbles. We have some more defects, but sometimes we notice that the bubbles always appear in the same place of the sole. Even if we change temperatures, even if we change pressures, they might change a bit in space, but they will be there because the problem was the project of the mold. So also we can have welding lines. Welding lines are zones where the flow fronts are merging, and they will cause bad mechanical behavior in the soles in that zones, which may lead the soles to crack. Okay, so computational methods. We are using Open Inch Mold Sim Solver, which stands for Open Injection Molding Simulation. And there's the reference. This is not my solver made by me. Basically, we are dealing with a compressible fluid. So we cannot say that the density is constant. We cannot say that the mass conservation is only the gradient, the divergent of velocity equals 0. I'm using a volume of fluid method, 2 phase, 1 phase for polymer, 1 phase for air. The sum of the 2 phases must be equal to 1 in each cell. Then we have equation for mass conservation for 2-phase system, momentum balance, and energy equation. Okay, so regarding the viscosity models, polymers are not Newtonian. Their viscosity depends on shear rate, pressure, temperature, and we have to model that dependence. So this solver, comparing it to compressible interfoam, it has a viscosity model, which is called cross WLF, and it is that, the first equation. It depends on the viscosity at 0 shear rate, and there are some other parameters that we can actually find by perform rheological characterization and then the fitting of curves with the model. Okay, so to model the pressure, volume, temperature behavior, this solver uses an equation of state called Tate equation of state. So basically, it presents a relation between specific volume, pressure, temperature. Okay, and the equation is there. Okay, so we have a problem when simulating injection molding because we have some outlets at some parts of the soles, and sometimes we may not completely fulfill the sole because there could be mass loss through the exterior of our domain. And in order to avoid that, we use a permeable wall boundary condition, which was firstly presented in OpenFOAM 2106. Forgot to say that OpenISMOL team was made up in OpenFOAM 7. So basically what the boundary condition does is like, okay, we define a value of alpha, which is volume fraction at the boundary, and we say, okay, when alpha reaches, for instance, 0.5, close the outlet. So the polymer is not allowed to get out. Okay, we can define another value of alpha. It can be between more than 0 and until 1. Okay, so when that value is when the value of alpha polymer is less than the alpha that we define, we just have a 0 gradient for velocity, and then we have a fixed value of 0. The pressure is the opposite. Okay, so in the left side, there's the boundary condition. As I said, it was not made by me. It is present on OpenFOAM 2106. Bruno, which is there, he transferred this boundary condition to OpenFOAM 7. Here we have a movie that tells us what happened. Okay, so when the polymer touches, it's not touching, but when we have 4 outlets, and when the value in the boundary is higher than the value that I specified, the velocity goes to 0. So the air escapes, and then it closes, and the polymer doesn't escape. Okay, so we needed some values to put on the rheological model and cross WLF. So there were made some tests, rheological tests at University of Minho in our department. We have conditions to do it. Mainly here, there are represented some capillary rheometer tests. Basically, in a simple way, we have a piston that forces polymer into a kind of cylinder, and you have a die in the bottom, and basically it measures the pressure. So if the polymer is more viscous, more pressure will be detected. Then we perform tests for several shear rates, and we collect the data, which then then we fit the model with this data. So in case of the pressure volume behavior, I didn't perform any tests. I just stole some data from Moldex 3D proprietary software. In this case, the variation of specific volume with pressure is represented just for one temperature there. I didn't put more temperatures, but if I add a lower temperature, for instance, the volume should decrease. Okay, there is the first case study. We have a company that is part of the project, asks us to do a simulation with a simulation of polyurethane thermoplastic injection molding. They gave us the inlets, the outlets, and they said, okay, let's see how it works with a solver. These simulations I run on my personal computer. That next time I will increase the number of cells and run it in a cluster. But as we can see, there are problems because we have entrapped air in two different regions, maybe here in front and at the back of the shoe. So, okay, they ask us some solution in terms of mold project to avoid these problems. Okay. In this case, we have suggested two corrections in terms of geometry. One of the first correction was to delete this outlet and to push the inlet to that place. Okay. This was made to avoid that entrap there at the front of the shoe. And then we are also, okay, we also had some entrap there in the back of the shoe. So we decided to move these two outlets to the front and see if it would work. Okay, so again, we did the simulation with the same geometry, but not the same geometry. We changed the inlets and outlets, but okay. So in this case, we have no longer entrap there in front and in the back of the shoe. Okay, so this is a potential industrial application. Okay, we have another shoe here with one inlet at the front and four outlets, and this will be the next work for me. Right now I just have simulated the original geometry, and we can see that there is a welding line. We'll see here two merging fronts of polymer. Okay, this is, we'll have a welding line, not only one. If you notice here, another one for, okay. What this will cause? This will cause that a region where the mechanical behavior of the sole is lower. Okay, so in this case we still need to propose some corrections, and we will do it as soon as possible. Okay, so what are the advantages and the problems of using this solver? We can say that we have a correct position of flow front, because even we compare the results of one of the soles with a short shot that was provided by the company, and I don't have the picture here, but they are quite similar, so it is good. Also, the permeable wall boundary condition, which is part of OpenFOAM 2106, it is good, and it can replicate the real system operation. As a problems, we have an excess calculation time. Then we also have some problems with high velocity magnitude and velocity gradients, mainly in the air phase. Sometimes the simulations just blow because there are really high gradients of velocity. Okay, as a future work, we will try to solve these problems related with the velocity gradients in the air phase. Also, for my PhD, I will have to do more stuff. This is just a small portion. So first, I will have to calculate mold wall stresses and formations, and this is because nowadays we are using 3D printed molds and molds made by other prototyping techniques, and they are not so good in terms of mechanical resistance. So we have to simulate its behavior, and then also predict the final dimensions of the parts after cooling. The dimensions will be affected by the residual stresses due to the wide gradients of temperature. Okay, and that's it. Thank you.
So do we have any questions? The audience or online?
So thank you for the presentation. So actually, I never used this kind of solver, so I don't know, but one day for 90,000 cells and 8 cores seems a lot. Why is the computational time so huge?
Yeah, mainly because we are using compressible solver, so you cannot do some simplifications in the calculation. Also, this is not a Newtonian fluid, so the viscosity is not constant, and mainly those two factors are affecting the calculation time.
Any further questions?
Yeah, thank you very much for your talk. I just asked myself, how long would it take to fill the molds? So in this process, it should be extremely fast, no?
Depends on the mold, but usually I work in injection molding, but issue solves injection molding, and something between 10 20 seconds. Depends on the solve, depends on the material. Yeah.
Somewhat related to that question, just there would be, is if you increase or decrease the flow speed, what effect does that have on the a rate of occurrence of the problems that you're trying to resolve?
Regarding
injection.
the bubbles, the entrap there?
Yeah, like
I didn't test it in the solver.
Okay.
But sometimes we used to do it in industry.
Okay.
And the bubbles, the position of the bubbles is influenced by the speed of injection. But depending on the geometry, it may be just a little move. It depends a lot.
Okay. Are there any further questions? Otherwise, we'll thank the speaker again and get some coffee.
Thank you.